Today, we've got limits and continuity, super well understood, or if not, we're on our way to understanding limits and continuity. We have the intuitive idea of those things. Now we want to get some more intuitive ideas that's going to involve a little bit more mechanics. And we're going to talk about calculus in two questions. Given a function, here are the two questions. What is the slope of the line tangent to a function at a given point? And number two, for later on, what is the area under the graph of a function and above an interval AB on the x-axis? I don't need to hold any surprises. So the first one is derivatives. The second one is integrals. Those are the two big branches of calculus: differential calculus and integral calculus. And we start with differential calculus because we've made bad decisions a long time ago, and it's very hard to change things. So let's talk about this first question. So we want to know what's the slope of the line tangent to a function. So let's remind ourselves of what the slope is. This is the same slope that we had back in algebra. That's why we're using the same word. And what is the slope of a line? Simpler. No, simpler. Change in y over change in x. How much y is changing divided by how much x is changing. What's another way we think of change in y over change in x? Rise over run. Awesome. You've heard these things before. It's like you guys have been in a math class before. That's awesome. All right. Normally, I do not ask this because it's a terrible question, but does anybody recall a formula for the slope? No, that's the equation of a line. I just care about the m part. You're right, though. M is important. M is the letter that we use to represent slope because that makes sense because m is not in the word slope. What the hell? Maybe there's like a French word for slope that has an M. Or maybe a German word. I don't know. So I normally do not like to think about the slope formula, except in this one very specific circumstance. Does anybody remember the slope formula? Y2 minus Y1. X2 minus X1. So that's the slope of the line between 2 points. It's the change in Y divided by the change in X in kind of an explicit format. Subtract the 2 Y coordinates, divide by the difference between the 2 X coordinates. And that will give you the slope of the line from this point, X1, Y1, to another point, X2, Y2. And because of the way lines are, this ratio of the change in y to the change in x will be constant between any 2 points on the line. That's why we can get away with this with linear functions, because the slope is constant. This ratio of the rise to the run is constant on a line. How's everything? Yeah, we just had to remember like one thing from algebra. Set the Wayback Machine to elementary algebra, and like, oh, what's the slope? Rise over run. Change in y over change in x. Y2 minus y1 over x2 minus x1. So just a quick reminder, the delta represents change. So this capital delta The capital delta represents change. So delta y over delta x is an abbreviation for change in y divided by change in x. For those of you who are new to the delta. No, that's for the other part. This is where sigma shows up. Here's the thing though. When we want to find the slope, we need to look at the slope between 2 points. So calculating the slope requires 2 points. I need 2 points to calculate those deltas. For the most part, most of the time, this isn't a problem, but it's a problem now. I need 2 points to calculate my rise and my run. The rise, that's the change in y. And here's my run, which is the change in x. So the problem is I need 2 points to do this. But the question at hand, so why it's a problem, all of a sudden I switched to caveman syntax. Why problem? Tangent slope, only 1 point. I'm sorry, I can't do the whole class as caveman. It wrecks my voice. I've tried it before. Sometimes I come with a new voice at the beginning of the semester and try to convince everybody that's my real voice. But I use a different one in each class. So like in Calc 1, I'd be like all, calculus, 2 questions. Slope, tangent line, only 1 point. But in another class, I use just a completely different voice. I'm like, welcome to Calculus 3. Multivariate. And so when people start trying to figure out who the hell I am, so like, oh, you mean the guy that sounds like a caveman? It's like, oh no, that's someone else. And all of a sudden there'll be 3 different Professor Leaches. This is why this is a problem. We're trying to find the slope of a tangent line, and the tangent line only hits the function in 1 point. The tangent line only intersects the function at 1 point. Well, this suddenly got awkward. Find the slope of the line. Change in y divided by change in x. You get 1 point. Well, that's certainly. Everybody see what we want to do and why we have this problem. So here's what we're going to do. We're going to be like all, close enough. That's our strategy. Close enough. That's the strategy for all of calculus in both of these questions. We're just going to say, it's close enough. And we're going to look where things are headed. That's that limit business. The same question is going to happen when we want to calculate area, because the only area formula that we need is length times width. And then the function is going to be like, but the length keeps changing. It's continuously variable. So we just flatten it out. That's close enough. And someone's like, oh, that's not good enough. So you just make it smaller. Here's our strategy. So our strategy for dealing with this 1 point business. We're going to pick a point close to the one that we're interested in. Pick a point on the function close to the point we care about. Close to the point in which we are interested. Then we're going to calculate the slope of the secant line between those 2 points. Now we have 2 points. We'll pick a point on the function close to the point we're interested. So now that we have 2 points, calculate the slope of the secant line connecting those 2 points. This will be an approximation of the slope of the tangent line. So we do this, now we have an approximation of the slope of the tangent line. That's what we call a secant line. So if a line is tangent to a curve or some other shape, it only hits it in one spot. A line that cuts through, we will call a secant line. No, secant. Secant goes through place. Now, this is just an approximation. We need to know how to improve an approximation. Approximations are only good if we know how we can improve the approximation. So next, we run out of scannable space on our paper. We have to turn the page at this very inconvenient moment. So make sure you turn the page. Some people are like, oh, I just did. Do I have to turn another one? Yes. Yes, you do. Some people are like, oh, haha, I'm taking notes on a tablet. Michael, then you're going to have to get a whole new tablet. I'm just kidding. That would be ridiculous. Now that we have an approximation, we can improve the approximation by moving our second point closer to the one that we're interested in. Now we can improve the approximation by moving the second point closer to the one that we're interested in. Then we do the calculus thing. How close? Infinitely close. That's the calculus thing. The calculus thing is when you're doing a process that improves your approximation, just do that an infinite number of times. We're going to move that second point infinitely close to the first point. In the language of limits, we're going to take the limit as the difference between the 2 points drops to 0. We're going to take the limit as the difference between the 2 points approaches 0. We're going to see what happens as we continue to make the points closer together. That's another way to think about it. What happens as the points get closer? We're asking ourselves, what's happening as the points are getting closer? Where is the slope of the secant line headed? So the limits of the secant, the slope of the secant line should equal the slope of the tangent line. This is how we will rigorously define our derivative. Pause for comment. So I'm not supposed to read that part. How's everybody okay? So the limit of the slope of the secant line will become the slope of the tangent line. It's a long pause because this is a TED Talk moment. TED Talk moments happen when like the speakers are going blah, 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 blah. And so if I was doing a TED Talk version of this, when I got to the limited secant, the slope of the secant will become the slope of the tangent. And you move your hands out like this, the sides, like you just did something amazing. Use your I just did something amazing voice, and then people applaud, whether they understand what you're talking about or not. It's most fun in science TED Talks because they're like, oh, I and 4 other people in the world understand this topic. Let me present it to you, the TED Talk audience. And everybody in the audience is like, oh, yeah. Meanwhile, they're like, oh, you know what he's talking about? I don't know. I'm just kidding. That's just me projecting. Because a lot of times in a meeting, I'll be in a faculty meeting, people will be talking about something, and I go, I go, what? I thought, here's this policy. And they start talking about, and I'm like, oh, in my mind, I'm like, oh, W, T, yeah. But outwardly, I'm like, oh, yes, I see where you're coming from. Yes, that's very important. We should implement this right away. We're talking about getting rid of something, Leach. Oh, I mean, we should implement getting rid of it right away. Nice recovery. What are we talking about? Oh, yeah. Let's draw a quick sketch. I know I should draw a slick animation, but I don't draw slick animations. I draw quick sketches. We've got a function that I'm going to exaggerate its curvature. So I have some room. At one point, we're interested in this. This is the thing that we're looking for, the slope of this tangent line. But the stupid tangent line only involves this one point where x equals c. So I've got one point where x is c, and I know the value of the y-coordinate by plugging in the function. So that point here is c comma f of c. We try to calculate the slope at that point, and we're like, oh, dang it, we've only got 1 point. Delta y over delta x is 0 over 0, and this is not defined because it could be all kinds of different things. I can't do 0 over 0. So we pick a point that's nearby. And we're like, well, hey, you over there, a little bit away. Now, clearly, this has been exaggerated because this is a terrible approximation. But I'm going to take this point that's a little bit a ways away. I want to use my starting point, my c comma f of c, as a starting point. So I'm going to write how far this one is relative to the previous one. I'm going to say this is h units away in the x direction. So the coordinates here are going to be oops. I'm going to pick some x coordinate that is close to c. I'm going to say this is where x is equal to c plus a little bit. H is the traditional difference between these 2 points. So the coordinates at that point are c plus h comma f of c plus h. And I want to find the slope of the line between those 2 points. So we've gone h units away horizontally from the point we're interested in. This other point. Now we have 2 points, and so we calculate the slope, just like in the instructions. So our slope is y2 minus y1 over x2 minus x1. change in y divided by change in x. We did not specify what's going on with the function, so I can't simplify the numerator any more than it already is. But we can simplify the denominator because I've got c plus h minus c. So we have f of c plus h minus f of c divided by h. Just calculating the slope of that secant line. Then what we want to have happen is I want to move that point closer to the point that we're interested in. So I'm going to squish h, make h smaller. So I'm going to take this point and move it closer. I want to move that second point closer. So that secant line will just line up with the tangent line when h is equal to 0. But we notice h can't equal 0. Otherwise, we just have 0 over 0. And that's not defined. So we have to say, how can we plug in 0 in the denominator? That was way too early. We'll take the limit as h approaches 0. So we'll plug in a bunch of values for h and see what happens. So the slope of the tangent, oops. The slope of the tangent will be the limit as h goes to 0 of f of c plus h minus f of c over h. And this will be a very particular 0 over 0. Any questions? This is the thinking that is going to be running behind this slope of the tangent line business. This is the thinking that goes behind it. That's why I want to put it out there now so that we can get on with some mechanics and not have to worry about the thinking in the foreground. Just let the thinking run in the background while we're doing mechanical stuff. Okay. Correct. It's not actually 0, it's infinitely close to 0. And you're like, oh, well, how far is it? It's 0. 0, 0? No, very close to 0. Like 0. Very close. How big's the difference? 0. But then it's very close. It's infinitesimal. If you're thinking that this is kind of a fishy maneuver on our part, that's only because this is kind of a fishy maneuver on our part. Like that whole business with the limits, we had to come up. That wasn't what we started. That wasn't what we started with. That's what was forced upon us by people like Weierstrass coming along. This definition of continuity is terrible. What does that even mean? And we're like, oh, well, you know, it just means this. It's like, oh, yeah, but what does that really mean? And I go, ugh. And then finally we come up with this epsilon delta business. And I go, does that work? And Weierstrass is like, oh, all right. But anyway, this is the difference between putting your math class in the engineering department and your math class in the philosophy department. It's much more difficult in the philosophy department than it is in the engineering department. Engineering department is great. Shit just got to work. Philosophy department, stuff has to make sense. And then someone's just going to be like, oh, but does it really make sense? Yes, here's why. But does it really make sense? Yes, here's why. But does it really make sense? Yes, wait a second. And then we just go on arguing. This is why I had to get out of engineering and into math, so I could just sit there and argue, and we could just wonder how wrong we are. Yeah, perfect timing. All right, that's gonna do it for today. Tomorrow, something more practical. That's gonna do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.